This screencast will explain how pressure in a fluid with no shear stresses varies from point to point. And what we're going to do is start by looking at an element of fluid with surface forces. So our surface forces are going to consist of pressures, forces, as well as our body forces, which are going to consist of weight. So let's start with our surface forces, and we are going to designate right here in the middle of our differential element the pressure P. And we're going to express P on each one of the faces in terms of our P and its derivatives, which is actually doing a Taylor series and neglecting the higher order terms. So let's start by looking at the surface forces in the z direction. So if you've noticed, I've taken the top, which is right here, of our elemental cube, and the bottom. So the volume of our elemental cube, you can see, is dy, dx, dz. So again, we're looking at this top face, and we express our surface force in the z direction as P. So we're going to start at the center of the cube, and then we're going to go up. We go dp dz, which is that change in pressure with respect to the z direction. And since we're going halfway up the dz side, we multiply that by dz over 2. And because this is a force, we have to multiply it by the area that this force is acting on. Now let's look at the bottom. So here, again, we start with our P, and because now we're going in the downward direction from the P in the center, it's minus our dp dz times this differential length, all multiplied by our area. So if we put these together, what we're looking at is the force that's coming in minus the force that's coming out. That's P, okay, because we're going in the positive direction, minus dp dz dz over 2, minus P plus dp dz dz over 2. All of that is multiplied by this dx dy, and this is going to be the force in the z direction. As we look at this, if we take this and do the algebra, or actually it's subtraction and addition, we end up that this is minus dp dz times dx dy dz. Because right here we have this P minus this P, and then this is a negative minus a positive, so we add them together, and that's why we get the dz over 2 plus dz over 2, which is our dz, times our dx dy. And we do this same thing for every other face, and we'll get the same expressions except how P varies. And dfy is equal to minus dp dy dx dy dz. Now if we write this in terms of a vector, so the total surface forces here, it's going to equal minus dp dx, which is in the I direction, or the x direction, plus dp dy in the j direction, plus dp dz in the k direction, and this entire expression is multiplied by our dx, dy, and dz. If you notice these dp, dx, dp, dy, dp, dz terms, we can actually write this as del p, where del equals d something dx in the I direction plus d something dy in the j direction plus d something dz in the k direction. In our case, our d something or our something is p. So now we can rewrite this vector here divided by the volume as minus del p. Now we have to look at the body forces. The z-axis is vertical. The weight only acts in the vertical direction. So what we're left with in our body force as minus the differential weight in the k direction, which can be written as minus the specific weight times dx, dy, dz. Notice it's only in the k direction. Again, it's negative because the weight is in the negative z direction. Now let's apply Newton's second law to this. And again, it's to the fluid element. So the sum of the forces equals our mass, our differential mass, times acceleration. So we can write that as our surface force minus our weight, which is only in the k direction. So when we put this all together and simplify it, minus del p times our differential volume minus our specific volume times our differential volume in the k equals, and now we're going to change this mass into rho dx, dy, dz times acceleration. Dividing through by volume, we find that minus del p minus the specific gravity in the k direction equals rho times the acceleration. And this is the equation of motion with no shear stresses.